Good morning. Welcome to Krishna's class. The theme of today's talk is the uniform boundedness discipline. It's also sometimes called Banach's house theorem. Now, before we discuss the or give out the statement of the theorem and then go ahead discussing the proof of it, we will first look at some motivating results, which are from a general setting or something that is familiar with all of us in analysis. So let us look at this example. This example is interesting. Let a real valued function on the compact interval 0, 1 be defined by xn t equal to n square t 0 less than or equal to t less than or equal to 1 by n and 1 by t for 1 by n less than 1. Now, it's very easy to know that this is a continuous function for each n. This is for now, if you look at the graph of this function, it is like this. So, at 1 by n, take the point 1 by n, n. This point is 1 by n. Now, on the interval 0 to 1 by n, it's a straight line segment that joins 0, 0 with 1 by n. And on this part, this is going to be 1 by 1. This is a point 1, 1. And this is the part of the 1 by t, xt equal to 1 by t on this interval 1 by n2. Now you can see that this is your xn. If you want, you can mark it with a different color to get a feeling. Now this is the straight line segment and this part is the function 1 by. So you see that as n tends to infinity, that means 1 by n goes to 0, you see that this goes to infinity. But otherwise, this is a continuous function and you have the following properties. Okay. xn t is etc. So xn t is a continuous function. And xn 0 equal to 0. xn 1 by n equal to n. And what you have is this mod one by n. So it's a bounded sequence. Sorry, it's a function. Each function is bounded. Okay, so each xn is is a bounded function on the compact interval 0. Now we observe that x and t, if you take the whole class of functions x and t, this connection of t belonging to 0, 1, this is not, it is not uniformly this is an often invoked example to highlight the phenomena of a bounded sequence of functions need not be uniformly bounded. Okay, so that is one thing. So naturally you should ask the reason why it is not uniformly bounded, or what more you need to get this uniformly, get such a sequence uniformly. So the question is, now this is one of the natural questions that comes at this stage. Now we have a more general theorem. We have the well-known Ascolis theorem. Now the statement of the theorem is, let T be a compact for instance, you see that 0, 1 is a compact subset of R, and if you take the relative topology, this becomes a compact metric space. I mean, in fact, R is a metric space. You take that metric on the compact interval 0, 1, this becomes a compact metric space. So let T be a compact metric space. If Ct is bounded, this is the continuous functions on the interval T is bounded and equicontinuous on T, then it is uniformly bounded on T. So equicontinuity is not just the boundedness of the continuous functions that is required, or the class of functions that you take is not sufficient to be just simply bounded, but also should be equicontinuous on T, then it is uniformly bounded on. What do you mean by equicontinuous? Now when you talk about continuity, you see that you have this property, that is f or ft minus given epsilon positive, there exists a delta such that now what happens is that, see, suppose you are taking a sequence of functions, then you see that this is continuous if for each n this is true. That means what? This delta would in general depend on, okay? So this delta would in general depend on it, because we are assuming each of these functions is a continuous function. So what you have is this. You have a sequence of continuous functions. You have a sequence of continuous functions. So you have a sequence of continuous functions. Fn, say each Fn is from T to R, say. Okay. Now assume this, or you can even replace R by another metric space. Now in that case, what happens? This is what you have. The distance given epsilon positive, there exists delta positive such that and this delta essentially depends on epsilon, and of course for each n, so this is in general depend on epsilon and okay, right? So it's a continuous. So each one is a, that is each Fn is continuous. But now we assume the sequence Fn, or the collection of functions, is equicontinuous if for every epsilon positive there exists a corresponding delta depends only on epsilon and not on such that delta depends on epsilon. Now it is not dependent on delta is available independent of that is the availability. Now you see, you can talk about Fn as a map from T to some other metric space. Okay, and then have this same kind of because then mod T minus S will have to be replaced by the distance between T and S. That is the difference. Okay. Not only that, then all this statement will go. So then if then the collection Fn is equicontinuous. Now this need not be a sort of something like Fn, but you can also talk about F alpha. Alpha is an index set. And then of course you can replace all these things. Delta is available independent of alpha. Replace n by alpha. So the same statement would hold, and this is how equicontinuity is defined. Therefore, we are assuming that each of these functions is not only continuous, but the entire class is equicontinuous. If that is the case, the conclusion that we make in the Squiggly's theorem is that Squiggly's theorem concludes that the collection or what you call this entire collection CT is uniformly okay. So that is the result so that goes as a generalization of the first result that we have. Now the question that you are asked is this. We have said it is uniform. We are asking the same sort of question here in the context of what are called a bounded collection of bounded functions in a Banach space. So uniform boundedness. So uniform boundedness. Yeah. Give the statement. The statement is this. Let in fact, there's a restriction that we have brought in here because we are assuming that X is a vector space, which we are not assuming in the earlier results that we have quoted. There we are just taking what are called metric spaces, and we are assuming the domain T is compact. Okay, right? Therefore, it is automatically complete. Okay. So here we are assuming X is a Banach space, which means X is a normed linear space, and it's a complete normed linear space with respect to the metric induced by the noun. So let this is not the statement of the theorem. You are just then if you are talking about that every bounded linear map is continuous. So you are talking about what are called continuous maps from X to Y. Okay. Now we can state the theorem. Suppose Banach space and Y a normed a Banach space is a normed linear space which is complete, whereas we are not assuming that the range space is not complete. All that you need is it is a normed linear space. Okay. Let lambda alpha belonging to some index at A is a collection of bounded linear transformations bounded linear transformations are the continuous linear transformations of X into. So you have now a collection of bounded linear transformations with the following properties. A is an index set. Then either there exists a finite non-negative M such that for every alpha belonging, or what you can have is this supremum of This is it. This is unbounded. Okay? For the supremum of lambda x, norm of lambda x is unbounded. Now here you recall that okay, for every x belonging to a G delta set, which is the intersection of a countable intersection of open junctions, and a G delta set need not be so that is the statement of the theorem. Now just recall so this is how the norm of the linear transformations, bounded linear transformations is defined. Now you see that you know that you take the class of all bounded linear transformations from x to y. You know that you can talk about addition and scalar multiplication in the natural way. What is the natural way? The natural way is, you see, what is the rule of addition? The rule of addition is take this, you define belonging to the field. Okay, so this is it. So it is linear, and what more? Therefore, the collection of all. So we have got BL to take the all bounded linear transformations and then produce addition like this, then it is going to be it's a linear space. So this is a linear space. This is linear. Further, now you define supremum of lambda equal to 1, then lambda. So it's a so with this you see BL XY with a it's a normal linear space. Therefore, it's a metric space. Okay. with the definition that D of equal to okay. So these are the basics that you have. So what we have is, I mean, these are the vital, definitions of the norm, etc., of the operators. Now before we go to the proof, we'll just look at the geometry. What is this? So the two statements that you have, one is this one, this is second statement. Okay. So either there exists a ball P in Y radius such that lambda alpha maps the unit ball x into b. This is one part. Okay, so that's the first part. This is one. This is the first statement interpreted, or in fact an entire G delta. G delta means the following. It is the intersection of, it's a countable intersection of open sets. And you know that if you take finite intersection of open sets, you get an open set. But the moment you make it countable, or even something like whole collection, something like a collection B alpha belonging to some index set which is not finite, then the intersection need not be an open set. And what does it mean? And such sets are given a name. It's called G sets. Okay, so this is what you have, such that no ball of radius for every alpha. Okay, so this is the interpretation of this, the geometry interpretation of this here. So we'll pass on to the new focus. What we do is, okay, let us look at some examples. For me, two examples, huh? So x equal to r, y equal to r. Define even r, right? We define T alpha x defined as or what you call phi alpha psi alpha x, right? Where psi is a where of course alpha belongs to an index set A. So A is an index. So psi is a map from the index set R. Assume okay, let us confine ourselves to the following. Let the interval 0 1. Choose this index set. Okay. Then we have T alpha psi alpha x, and we assume bounded function, bounded function, bounded by then x belonging to and what is this? This is equal to and mod psi alpha is less than or equal to m. Therefore, this is equal to less than or equal to m times. So you have I'll say sorry. And this is equal to therefore lambda alpha is less than or equal. Therefore, if psi alpha is bounded, then this is bounded by particular m, or this collection is uniformly bounded. That's the result. Okay. Now a second example. Can we take the index set? That is the index set. Okay. So define equal to, now each lambda alpha is a linear transformation, it's also bounded. It's a bounded linear transformation. But it's a bounded linear. Each lambda alpha is a bounded. Okay. That is because or in fact this is equal to however it's not uniform. Hold it. So let us prove this here. Uniform boundedness theorem. Proof of the uniform boundedness theorem. Set as supremum alpha belonging to A x belonging to x. Now you consider the following set. So this is the definition of phi. Using phi, we define the following set. Define the following sets. Vn is defined as set of all x for which greater than, that means the set of all x which has the property that phi x is greater than n. That means this is phi x, so this is greater than such x you take. Now let us look at the properties of this. Now each y since lambda alpha is continuous, and the function norm on is a continuous function, what we have is, this is a combination of the two things. You have lambda alpha x and norm. So it is norm combination with lambda alpha x. Okay. So norm with lambda alpha is the composition that comes. They are two continuous functions. Therefore, it is a continuous function. Therefore, the function x2 So this is a continuous function. Okay. Now we will look at this. For the definition of phi, phi is defined as phi x equal to supremum alpha belonging to A of norm lambda alpha x. It follows that phi is lower semiconductor, and consequently and that is the explanation for openness of. Now suppose one of these sets Vn fails to be dense in X. Say Vn is something like this. Then comes. See, Vn is not dense in Vn is this. This is V. Rather it is easy to draw this. If so, there exists an x naught belonging to and some are positive such that for norm x less than r, x naught plus x does not belong to taken, because you see that this is, we are assuming this is not dense, okay, or fails to be dense in X. Therefore, this is true, and or this is simply taking the interpretation of the definition of phi that we have. Okay, now what does this mean? Now you see that equal to X, therefore less than R. So now let us compute this. Then lambda alpha X naught. This is something that follows from that this is equal to so. So, and you have, if you take lambda alpha on it, you can see that it is linear, therefore you can write it as lambda alpha of this minus lambda alpha of this. Now you take the norm. What is the meaning of that? Meaning of this is the following. It's less than or equal to 2, because each one is less than or equal to 10. Go for the definition of phi. So now choose two n by r, then that you can easily work. Okay, so if you take norm x less than r, then you see you can make an inequality from here, use this inequality, and from there you can get, take the supremum, you get everything. That is the method. Now that is one possibility. Another possibility. So that proves the first part. The other possibility this is the example to that particular example. The other possibility is that every then say next. Intersection Vn is a G. Now you take, therefore, it's a G delta set. By Bayes' theorem. This is where we apply it. Okay. En, we have greater than n, and consequently this is true for every x, that is phi x has to be necessarily equal to n. What is the consequence of that? This is not uniformly bounded. That is so in the first example that we looked at, lambda alpha is uniformly bounded, and the second example, lambda alpha is not uniformly bounded. Okay, I think I'll stop here. These reports. Thank you very much.